Lab 3, Road Ripper, presented by Group 7. Your presenters today are Brianna Callie, Samuel Coons, and Jaron Rochester. Today, we are going to demonstrate a possible implementation of a truth table for an automotive signal light control circuit using either AND or and NOT gates, or using a read-only memory, ROM. Such a circuit would have controlled the signal lights of many cars, such as the pictured 1969 Mustang Shelby GT 500. Here is the truth table for this control circuit. We will demonstrate the simplification of the Boolean expression for the left back signal light, highlighted in yellow. Highlighted in green are the various input combinations that will cause the left back light to operate. Below the table is the unsimplified Boolean equation for the left back signal light.
The easiest way to simplify the Boolean equation is to use a K-map. Here's the K-map for the left rear signal light. In green, we see that the S and R terms change, while the C and L terms do not. Thus, we have C and L. In red, the L and C terms change, while the R and S terms do not. Thus, we have R and S. In blue, the R and C terms change, and S and L naught do not. Thus, we have S and L naught. If we OR these together, we get the simplified Boolean equation for the left rear light, shown here as C and L, or R and S, or S and L naught. Using the same technique, we can find the equations for the other lights shown in the table. Here is an implementation of all the signal marker Boolean equations into one circuit. Since the C and L term is used in both the left front and left rear signal, we can use the same AND gate to AND C and L together for both signals. This helps reduce the number of gates required. The same is true of the C and R term. Notice that this circuit uses a total of 2 NOT gates, 6 2-input AND gates, and 2 3-input OR gates. Here is an implementation of the circuit using a ROM instead of the gates. Notice we now have just one component on our board. While the ROM looks neat on a diagram, it must be programmed to function properly. Here's the truth table again. Notice that the inputs and outputs have been translated to hexadecimal numbers. For now, let us look at input row 8. Notice that the input of the various signals has been converted to a hexadecimal value of 5. To program a ROM, we insert the hexadecimal value of a row into that position in memory. In our example, we would program a hexadecimal 5 into the 8th position in memory. Now, when input 3 is high, input 2 is low, input 1 is low, and input 0 is low, this would represent a value of 1000, or 1000 in binary, or 8 in hexadecimal. This would trigger the ROM to output the value within the 8th position of the memory. Since it had been programmed with a value of 5, the ROM would output 0101, which is the binary equivalent to 5. This would mean that the third output would be low, the second output would be high, the first output would be low, and the 0th output would be high. This would be repeated for each row of the truth table.
Now we can test the circuit. Here we see that the inputs R and S do in fact cause the left back signal output to be high. And we see the same output with the ROM. Here we test the CL inputs and on the gates and see that the CL inputs do cause the left back signal output to be high. This also causes the left front output to be high as expected. As we see the same output with the ROM. Here we test the SL naught inputs on the gates and see that the SL naught inputs do cause the left back signal to be high. This also causes the right rear output to be high as expected. Again, we see the same output with the ROM. As demonstrated, using gates or a ROM can deliver the same results. Either technology could be used to create a vehicle signal control circuit. While the vehicle signal control circuit could be created using either gates or a ROM, using a ROM will reduce the number of components needed, which may reduce the cost and increase the speed of the circuit. Thank you for your time. We hope you enjoyed this presentation of the Road Ripper Lab.